Hello and welcome to the 43rd lecture in this series. So I'll start by completing the calculation that I was doing last time. So I wanted to describe integral curves of left invariant vector fields in GL and R, and for that I need the notion of the exponential of a matrix. So I was in the process of proving that if I start with any matrix in M and R and then look at this power series in T, n squared, actually the entries of this, the n squared entries of this matrix will claim as they converge uniformly. So I wanted to apply the Cauchy criterion, then I looked at the difference in partial sums between the ijth entry of Sn, S capital N and S capital M. By using the operator norm, I was able to reduce it to this thing here. Actually, I don't need to call it anything, so let me just say that we know that the exponential series, we know that sigma x to the power k over k factorial, k equals 0 to capital N, converges uniformly for any r greater than 0. We know that this converges uniformly in mod x less than r. So because this and this limit is what we call the exponential function. Well, so this is just what I have here is the difference in partial sums of this particular series for a specific choice of x. So the fact that this converges uniformly implies that, again, the Cauchy condition will imply that there exists n naught such that if m and n bigger than n naught, then the difference in partial sums, which would be, and again I'll assume m bigger than n, k equal to n plus 1 to m mod x to the power k by k factorial. This will be given, so I should say given epsilon greater than 0, there exists n naught such that if this happens, then this thing here is less than epsilon for all x with mod x less than r. So this is a fact from one variable calculus. So we know this, and therefore now what we have here is exactly this, where x has been replaced by t times norm a. But the condition on x is mod x less than r. So what we want is, so we know that this thing here k factorial less than epsilon, again m and n for any m and n bigger than n naught, but and for all t with modulus of t norm a naught less than r, i.e. mod t less than r by a naught. So in this open interval, this one has this estimate here. Of course, this r was arbitrary, so I could have taken r as large as I want. So I can take, if I start with an r, I can take a new r times norm a naught, and get the required r here. That's not a big thing. There's no restriction on r. So the statement is proved. So as I said, the point about proving uniform convergence is that I know that it will converge to each entry Snij will converge to Sij, which is infinitely differentiable, and moreover the derivatives of Sn will converge to the derivatives of Snij will converge to derivatives of Sij. We denote the limit of all the entries will converge, therefore the matrix itself will converge, and so we denote it by e to the power Ta. So e to the power Ta is differentiable, is C infinity as a function of t, and of course this is a matrix, so when I say it's C infinity, I mean that all the entries are C infinity and the derivatives are given by differentiating the power series term by term. So in particular, if I want the first derivative, d by dt of e to the power Ta, I just have to differentiate this the series expansion term by term. This will be, so d by dt of k equals 0 to infinity t to the power k by a to the power k by k factorial, and this is k t to the power k minus 1 a to the power k factorial, and then now of course k starts from 1 to infinity, so I can get out this, I can bring out this a1a outside and write it as k equal to 1 to infinity k t to the power k minus 1 a to the power k minus 1, this k cancels off, and then k minus 1 factorial, which is just a e to the power Ta again, by changing indices. So this is what we need. Derivative of e to the power Ta is a e to the power Ta, and this immediately tells us the following thing, that corollary of this derivative formula is that let sigma be the integral curve of xa starting at the identity, then sigma t is given by a e to the power Ta. proof is quite short. Well, of course it starts at identity because sigma 0, so I need to check first that it starts at t equals 0, and notice that this is defined for all t and r. So sigma 0 is a e to the power 0. Well, if I plug in 0 in for t equals 0, the only term which will survive is the 0th k equals 0 term, which is just I. So a times I, so this is a. Oh, sorry, this is not, I should not put an a here. The a will come after differentiating. So this is just I. Now the main thing is the integral curve condition. So we want to check that sigma prime t is equal to the value of the left invariant vector field xa at sigma t. So let's take the derivative for sigma prime t, and we have seen that this is the same as a e to the power ta, and this we know that this is the same as, well, first of all I want to write it, I can write it as e to the power ta times a, and I can do this because this e to the power ta is a power series in a. It's a limit as n goes to infinity. So when I multiply by a, essentially I just have to multiply all these powers of a by a. So I can do this on the left or right. So this commutation relation holds here, and what one has is right. So this is the same as the value of the left invariant vector field at the point e to the power ta times, no, sorry, I should put a here and then the value of the left invariant vector field given by a at e to the power ta. So I'm just using this what I proved last time, that the left invariant on GLNR, the left sort of this lemma, no, even, yeah, this lemma, that on if start with any a, then xa at any point p is given by pa. And this is the thing which I need, and so I've used that here, xa at this point e to the power ta. Notice that, so here actually I need to make a small remark that I'm working in, I'm trying to find integral curves in GLNR. So I should first of all, even before I do this this calculation here, I should perhaps remark that sigma t actually belongs to GLNR. We know that the exponential exists, I mean the power series converges for every t, but it may give rise to a matrix in just MNR which may not be invertible. So I want to ensure that I stay inside GLNR. So, and that's because I can explicitly write the inverse of e to the ta, e to the power ta times e to the power minus ta equals identity. And the way one sees this is that the fact that this is equal to identity is just again goes back to general properties of this power series. When you multiply two power series, you can just multiply the partial sums and then take the limit if they both converge. So I won't do this fact. So perhaps this can be a topic for the live session or the tutorial. So assuming this, I'm assured that sigma t belongs to GLNR for every t. A can be anything, no restriction on A. Whatever A is, this always belongs to GLNR. So that's the first thing. So right, with that in hand, then this one has this, and this is the same thing as XA, and e to the power TA is the same as sigma t. So we have the integral curve equation. Sigma prime t equal to XA at sigma t. So that gives. So integral curves starting at identity are easy to describe, and it's also easy to describe integral curves starting at any other point as well. So we already seen this, that we can just use left translation to take the integral curve starting at identity. So if this is the identity of, this is true in any Lie group. If I have an integral curve starting at identity, if I want an integral curve starting at any point P, all I have to do is multiply this integral curve by the group element P, and that will give me the integral curve starting at P. Okay, so that concludes my description of the various quantities that we have been talking about, various objects that we have been talking about for the specific, in the specific case of GLNR and its subgroups. Incidentally, so while before I finish this, I should just remark that if A belongs to, now let's take the tangent space to the other two subgroups of GLNR that we had were ONR. Let's start with ONR, the tangent space at identity to ONR, and we already seen what this is. This is the space of, it's usually denoted by small o, but with my notation it's kind of hard to distinguish, so I'll just write space of skew symmetric matrices. Then again I can, if I want to find integral curves for the left invariant vector field on ONR, I could have very well tried, I could try to just use the same integral curve. After all, I know that this the left invariant vector field, we already seen that on the entire GLNR, its values on ONR will be all tangent to ONR. So in other words, the left invariant vector field on ONR generated by is the restriction of the big left invariant vector field. Since that is the case, we know that e to the power TA, which is an integral curve, will have to lie in the submanifold because its derivative is tangent to the. But one can also see that directly. E to the power TA belongs to ONR. And same thing with SLNR. And the reason is, well, I can directly check e to the power TA times e to the power TA transpose. Oh, I can't use the small t anymore. I'll use capital T for transpose. Now the way the exponential has been defined, I can take the transpose inside to the exponent, and I get e to the A transpose. And again, using the fact that A and A transpose commute, using A transpose equal to A transpose A, what I get is this is e to the power t A plus A transpose, and that will be, since A is skew symmetric, this will be 0, so e to the power 0, which is identity. In other words, this e to the power ta is an element of On because it multiplied by its transpose is identity. So I should remark that it's a more general fact, which again follows just from power series, is e to the power a times e to the power b equals e to the power b times e to the power a equals e to the power a plus b if ab equals ba. Otherwise, of course, we cannot switch these around, or neither can we claim that we can add the a and b and get it equal to this. Similarly, if A belongs to the tangent space at identity of SL and R, this is space of trace 0 matrices, then e to the TA belongs to SL and R, i.e. det of e to the power TA equals 1. And this again can be seen by the fact that determinant of, so this is another separate small fact, that determinant of any matrix is equal to, rather determinant of exponential of any matrix, det of e to the power a is exponential of trace of a. Now, to see this is not purely a power series thing. So there are several ways of seeing this, and one is to use the fact that this equation is obvious if A is a diagonal matrix, and then generalize it to diagonalizable matrices and then prove it for all matrices by using density of diagonalizable matrices in all matrices. So one can do that. As I said, the fact that e to the power TA belongs to SL and R again follows, both of these statements that I have here follow from the more general fact that since the left invariant vector field on the big group GLNR is tangent to the subgroup at points of the integral curves will have to lie in the subgroup. One can prove that as a separate fact and then proceed. Then one wouldn't need to use this special matrix fact. Before I move on to the next topic of differential forms, so I would like to say a few things about the Lie derivative again. So the first topic is not the Lie derivative, sorry, the Lie bracket. An alternative description Lie bracket. So for this, what I would need is, I proceed as follows. Let xy be vector fields on a smooth manifold. Let's take a point P in the manifold. We know that by the Frobenius existence and uniqueness theorem, there exists epsilon greater than 0 and an open set U which contains P such that all integral curves of x starting at Q in U are defined on minus epsilon epsilon. So this is U, this is P. What I'm saying is that as long as I take a point inside this U, the integral curves which start at Q are defined on a definite size interval, minus epsilon epsilon. They cannot shrink to 0. Of course, as the integral curves may exit U, I'm not claiming that they stay inside U, just that the intervals of definition is at least minus epsilon epsilon. So for T for T let phi t be the flow, map. So be the flow of x. I had earlier talked about flows when I assumed that all integral curves are defined on the entire real line. But that's really not necessary. I can just, wherever we just need a fixed size interval. Then I have this, and only thing is that I cannot quite say that U goes back to U. So it's not a diffeomorphism of U back to itself, but rather a map from U to M. And its definition is the same. Phi t x is, you look at the integral curve which starts at x and move along that for time t. So this is the definition of. Now we define the so-called Lie derivative. Define the Lie derivative of y with respect to x. This is going to be another vector field on M by Lxy at the point P equals limit. So the idea is as follows. So I would basically, what I want to do is, well, so here's my point P. I travel along the integral curve for time t. So in other words, I see where the flow phi t takes this point to. At this point, I have the vector field y. So this is, if this is phi t p, and at this point I have y phi t p. Now what I'll do is I'll use phi minus t. So move back along the flow starting from here and end up back here. So that, and you take the derivative of that. That derivative will push this particular vector to something here. So this vector is d phi minus t at the point phi tp y phi tp. So I start with some vector here and use the flow, derivative of the flow to get back a vector at p. I can do that, and then I can just take the usual difference quotient. So then take the usual derivative basically. So I don't even have to write limit. So I just say, no, perhaps let me retain. So I'll just take the usual derivative. So in other words, I'll take d phi minus t of phi tp y phi tp minus yp, and then so this yp corresponds to t being equal to 0. So I'm going to take limit t. When t is 0, I know that the flow map is just the identity map. In this case, it's the inclusion map. So the integral curve sigma x at 0 is just x itself. So when I put t equals 0, I get this is just y phi of 0, and this is just identity map. So I get yp, and then by t. So in short, it's just the derivative of the first term, which I've written out like this. Okay, so we'll stop here. In my next lecture, I'll make a few more remarks about this Lie derivative. Of course, the main claim is that the Lie derivative equals the Lie bracket. So I'll just say a few words about that and then move on to another topic. Thank you.